Good morning, everyone. My name is Eric Romo. I am the DS23 tutor at Fresno City College, and today we will be talking about sampling distributions. So, what I wanted to talk to you guys before we get into this is a review of what a census versus sampling is. Now, remember that a census deals with a full population, and it is descriptive statistics because we know everything about our population. Our z-score is equal to x minus mu, which is mu, the mean of our population, sigma divided by sigma, which is our standard deviation, and recall the four reasons that we do not take a census. Now, those reasons were, again, the size of the population, our control and error, which means we can have a destructive amount of data, can be too time consuming, and it can cost too much money. With a sample, we have a sample size, which means that we take a portion of our population. Therefore, it is inferential statistics, which means that we infer things about our population from our small amount of our sample size. And z is equal to x minus x bar, which is our sample mean, divided by our sigma, which is our standard deviation, divided by our sample size and square rooted. Now, recall that sampling must take into account some error because we are not absolutely sure about everything of the population. This is why we call it inferential statistics. So the central limit theorem states that if the sample size is n sufficiently large, then the population of all possible sample means is approximately normally distributed, no matter what probability distribution describes the sampled population. Furthermore, the larger the sample size n is, the more nearly normally distributed is the population of all possible sample means. So what does this mean? Essentially is that even if we take a sample, if the population is normally distributed, then our sample size should be approximately normally distributed. So they should have similar shapes and therefore give us our sample mean, which should be equal to our population mean, and also our standard deviation should also equal our population standard deviation. Again, we have to take into account, however, our error. Notice that in the bottom of that z-score, let's go back there for a second, that in our z-score for a sample statistic, we have standard deviation on the bottom divided by the square root of n. So, which is right here in standard error, where sigma is the standard deviation divided by the square root of the sample size n, the equation above is what takes into account the error of the sample distribution. Always remember that a sample always has some error as it does not fully describe the population. We may only infer what the population statistics are from the sample data. Now let's go ahead and apply this logic. Looks like we have a problem here. A group of statistics students decide to conduct a survey at their university to find the average amount of time students spend studying per week. Based on a simple random sample, they surveyed 169 students. The statistics showed that the students studied an average of 14 hours per week with a standard deviation of 10 hours. What is the standard error? Alright, so that's my first question. So let's go ahead and bring this to the side really quick. Come on. Alright. Let's go ahead and close these little guys out. Alright, so first thing I need to identify in my problem, let's go ahead and zoom in a little bit on this as well. A little too much. Alright. There we go. So, first thing I want to look for are my knowns. So I know that my x bar, which is my mean, is any average or whether they specifically state a mean. So it says students studied an average of 14 hours per week. So my x bar then is 14 hours per week. It also states that my standard deviation is equal to 10 hours. Alright, so, and also my sample size, n, is equal to 169 students because they stated they surveyed 169 students. So my standard error, recall, standard error is equal to standard deviation divided by the square root of my sample size. So if I were to calculate this, 10 divided by the square root of 169. Well, I know that the square root of 169 is 13. Oops. So what is 10 divided by 13? Let's go ahead and look at that in the calculator. 10 divided by 13. Alright, so I get this long decimal. So let's just go ahead and keep it in fraction form as 10 over 13. Alright, so what is the probability the sample mean would exceed 17 hours per week? Alright, so they're asking for a specific point on my normally distributed graph. So this is my mean, which is 14, and they're asking would exceed 17 hours per week. So therefore, right here is going to be 17. Now they're not asking for the cumulative area up to 17, which would state people who study 17 hours or less. What they're asking for is right here, this unknown area. So what I need to do is I need to calculate my z-score. Recall that the z-score changes for a sampling distribution. Alright, so I already know my the bottom of my equation because I just calculated it, which was right here, 10 over 13. So I need to calculate the top. So 17, which is equal to my x, I should write that right here, minus my mean, which is 14, divided by 10 over 13. This becomes 3 over 10 over 13. Alright, so let's go ahead and put this in the calculator. I get 3 divided by, in parentheses, 10 divided by 13. I get 3.9 as my z-score. And no running decimals. Alright, so that means I need to go to a z-chart. Now some of you may also have a calculator. You may plug it into your calculator for your z-score calculations. Alright, so let's pick this one. Alright, let's go down. It was positive 3.9 with no running decimals behind it. Well, let's see. Uh-oh. It looks like we are higher than 3.4. That is exactly where the z table stops. So, what this means is that no students would be going higher. So no one would exceed because the entire chart has a z-score of exactly 3.4. Right, so as we can see right here, 3.4.9, so anything above that is already at the 100%, or almost 100%. So here I would write no one would exceed. Except a very, very small amount, which would be 0.000000001. Alright? So, and that's, for that example, let's go ahead and change that mark downwards. Let's bring it down to, what if they want to study 15? X is equal to 15. Alright, so this was 15. This would become 1. And our new z score would become 1 divided by parenthesis 10 divided by 13, which is 1.3. Alright, so if our new z-score is 1.3, I gotta go to my chart. Alright, so it says, and there's no running decimals behind that number, so it's 0.9032. So my area right here is 0.9032. Now remember the question asked if it exceeded that amount. Well, what I have to do is that I'm looking for the area not up to the 15. I'm asking for the area above the 15. So what I need to do is I need to take 1 minus 0.9032 because my entire graph cumulatively adds up to 1. So what is that? I get 1 minus 0.9032, which is this number right here. 0.0968 is the probability that a student will exceed 15 hours on average per week. And that's all there is to it.